Hello, everyone. Welcome to Calculus. My name is Scott Grizzard. This is lecture 6A, the chain rule. I am. Don't forget, we are on Twitch chat, and we are in Discord chat. So if you want to have, if you want to keep everything private within the class, there's Discord chat as well as Twitch chat. Okay, so tonight, what we're going to cover is the chain rule. And last time we covered the product rule, and I hit the microphone and all of those other things. On a personal note, a very exciting piece of news: the air conditioning just got installed, and it's starting to cool off up here at last. So we're going to go with the light too. All right, that's just a personal note. So what we want to do is we want to handle things like these functions here. All right, so let's go ahead and look at what we're looking at. Let's see. Okay, so what we want to handle is we want to handle functions that look like this. Now, let me turn off the camera here for just a moment. So I can zoom in here. Here, we have y equals sine of x. And then if I take dy over dx... when x equals 0. So I want the derivative of this when x equals 0. So I plot my little ruler down, and I take this little, the tangent line here, and I wind up with a tangent line of 1, or a slope of a tangent line of 1. Okay? So I've got dy over dx when x equals 0 equals 1. Right? And I can work that out as follows, right? Dy over dx equals the derivative d over dx with respect of sine of x with respect to x equals the cosine of x. And then the cosine, so f prime of, so dy over dx when x equals 0 equals the cosine of 0, which equals 1. All right, so how do we feel about that, 1 to 5? How do we feel about just, the slope of the tangent line is 1? How do we feel about that? Ooh, there you go. Okay. What happens if what happens to sine of x equals 2x? And that's an interesting question. So here I've got the slope of the tangent line at x equals 0 is 1. I take, that's the same as the cosine of 0, right? So I took the derivative of sine and I got cosine. And then I plugged in 0 and I got 1. Now, let's look at what happens if we do sine of 2x. So now if we do the same thing, what is the slope of the tangent line at 0? We actually wind up with a very different answer. Well, it's not that different. We're going to wind up with this. Right? And it's a steeper tangent line, isn't it? Right? Here, we had this nice flat line. Here, it's steeper. So what I need to do is I need to account for this doubling here. So in essence, this is moving around the unit circle twice as quickly. right? So the sine, of course, measures the movement around the unit circle. So on one of them, I'm just kind of going, yeah, and the other one, I'm going, right? I'm going much faster as I go around. So this runner is essentially running twice as quickly as this one. So the question is, how do I deal with that? Because you can see here that the slope is m equals 2. Okay. And to do that, we need to kind of invest in the journey of x a little bit. Okay? So that's sort of the setup. So let's invest in the journey of x. Let's look at a different problem. So let's look at f of x equals cosine of x squared. Okay. What is the journey of x? So before, when we had products, we had this kind of journey of x where x came in here and then x came in here, and then the two, something happened to them and then they got multiplied together. Well, now I've kind of got one route for the moment. But what happens? I plug in x here. So if I plug in pi, let's plug in 0. So if I plug in 0, first, 0 is squared. And then I take the cosine. So I would get cosine of 0 squared equals cosine of 0 equals 1. So here, what is the journey of x? Well, the journey of x is that first x comes along, he gets squared, and then cosine is applied. And this is called a chain. Okay. How do we feel about that 1 to 5, the kind of journey of x? Okay. So this is how we do it, right? This is called a chain. So the way that I'm going to deal with this is called the chain rule. Now, the way the chain rule works is this. Okay? I have a function that goes from some x space to a u space to a y space. And your book calls this function f and this function g. So g takes things from x to u, and then f takes things from u to y. And I want to know what happens, what's the total action? And the answer is I need to account for each little bit of change and then multiply them. So here I'm going to have an f prime. Here I'm going to have all this. So the whole thing is going to look something like this. I'm going to take x is going to go to u, and it's going to have, this will be g. Now there'll be some space called du over dx. And then there's going to be a space here that's going to take f here. F is going to take u to y, so there's going to be a dy over dx. I'm sorry, dy over du. And then what I'm going to do is I'm going to multiply them together. Okay? So dy over dx, which is the whole change, equals, right? This is from x to y. So the entire change is going to be dy with respect to u times du with respect to x. And I'm writing them in that order for a reason. Remember, you read function, right? So I read functions on the, when I do it, I'm going to compose functions this way, right? I say f composed with g, because it's f of g of x. So that's why we write them in that order. Okay. Let's go back to our example. So here, x went to x squared, and then x squared went to cosine of x squared. All right. So let's go back to our example. Okay. We had d over dx. We wanted to know the derivative with respect to x of cosine of x squared. So what I'm going to do is I'm going to account for this change by calling this a u. So now what I'm going to have is d over dx of cosine of u. Now, my chain rule says that I need to take the two things and I need to multiply them together. So what I'm going to do is I'm going to take d over du of cosine of u. I'm going to multiply. So this is the change I get from cosine. And then I'm going to multiply the change I get from x squared. So this here becomes negative sine of u times the derivative of x squared, which equals negative sine of u times 2x. And since I made u, I'm going to sub back in u, and I get negative sine of x squared. I have to make that simplification because I made u. And then that's the answer. How do we feel about that 1 to 5? Okay. All right, so let's state what the rule says formally. The chain rule. Recall that f g of x equals the thing closest to the f of g of x. So G happens first. Okay, so this states if not that much. If f is differentiable at g of x and g is differentiable at x, then f composed with g is differentiable at x, and the derivative with respect to x of f of g of x equals the derivative with respect to u of f of u times the derivative with respect to x of u, where u equals g of x. Now there are 1,000 other ways to say that. This is the way that I like to say it, but there's another way to say it. I could also say something like this: x to so alternate. So this is Leibniz. So I could say x to u to y, and then dy over dx equals dy over du times du over dx. I've also seen this done. So I go x to u with f. I don't even mention g. To y, and then I do the derivative with respect to d over dx of f of u equals the derivative with respect to u of f of u times the derivative with respect to x of u. These are all equivalent, except, of course, I actually mentioned the conditions on the first one. Okay. Let's look at another example. Okay. So let's do f of x equals sine of x. Okay. Then, so f prime of x equals the derivative with respect to x of sine of x. Now, I can't just do sine of sine, but I can take the derivative of sine with respect to the inside itself. So what I'm going to do is I'm going to do this. So then what happens is I get d over dx of sine of u. Now that, because of the chain rule, now I apply the chain rule. So I have it in terms of a u. So now I do the derivative with respect to u of f of u times the derivative with respect to x of u. And I'm only going to do these one layer at a time. So the journey of x here is like this. So I'm going to set u equal to that. So what I'm going to do is I'm going to take the derivative here. I'm going to do d over du of sine of u times the derivative with respect to x of sine of x. I'm sorry, not sine of x, of u. It will be sine of x, but not yet. Now, note what happened here. This was an x. This is a u. This is an x. Okay? I need this thing to be in terms of u. And that's what the chain rule allows me to do. Okay? Now I've got cosine of u times the derivative with respect to x of sine of x, which was u, equals the cosine of sine of x. I sub in for my u times cosine of x. I evaluate that derivative. All right, so how do we feel about that 1 to 5? Okay. Let's look at one more. Okay. Let's let f of x equal exp of exp of exp of x. Okay. This is an example of a double chain. Okay. All right, so what's the journey of x here? We've got x, I exponentiate x, and then I do that again. And then I do it again. That's fun. Well, what I'm going to do is I'm going to work outside in. Okay? And I'm just going to apply the chain rule. Now, I'm going to have to do it twice, but I'm only going to work outside in. Okay. So the first time, I'm going to let u be this whole chunk. So then I'm going to have the derivative with respect to d over dx. So I've got d over dx of exp of u equals d over du of exp of u times the derivative with respect to x of u. Now, this can be evaluated, right? Because now I've got u and u, they're the same variable. And this is a chain. So now what I'm going to do is I'm going to have an equals exp of u, because recall that the derivative of u is, the derivative of e to the u is e to the u, times the derivative with respect to x of u, which was exp of x. Okay. Well, now I'm going to go in again. So notice my derivative problem is now easier, right? I've got this term where no calculus needs to be done. And now I've got this term where I still need to do calculus. So my problem now is this. This becomes my baggage. So I have to carry this, but I don't have to deal with it anymore. And this right here is the problem I have to deal with. So the problem is now shorter and easier. Okay. So let's deal with our problem and carry our baggage. Okay. So now what I'm going to do is I'm going to do another run of the chain rule. But this time I'm going to let this be v. So now I need to carry my baggage. And I already used u, so I'm going to use v. So this is going to be times the derivative with respect to x of exp of v. Okay, carry my baggage and apply the chain rule. This is baggage. Now I apply the chain rule. So I got d over dv of exp of v times d over dx of v. Now, the derivative with respect to v of exp of v is simply exp of v times the derivative with respect to x of v, which was exp of x. So that equals exp of u. Now, this is baggage. This is what I have to deal with. And so I've got exp of u times exp of v times exp of x. Now my calculus is done. I just have to sub in what I did. So this became exp of exp of x times exp of v, and v was exp of x, times exp of x. Okay, how do we feel about that one, 1 to 5? That one's a hard. This one's a double chain. So I have to apply the chain rule twice. One to 5, how do we feel about that? Okay. Nobody's voting, and the person taking the votes is also not paying attention. There we go. Okay. All right. So, if you open your notes, okay. So let's talk about the proof. Now, it should be noted that I'm going to assume that f is somewhat well behaved. So I'm going to assume that f does not have an infinite number. I'm going to assume that f does not have an infinite number of places where f of x equals 0 near that. I'm going to demand that the change in u not equals 0 near x. And that's it's gonna limit us. It's not the full proof. There's a full proof. It's in the book, but it doesn't really enrich our lives. Okay. So what we want to talk about is we want to look at the proof. Look at the proof, and we want to do the intuitive proof. We don't want to do the proof where note not full version. So the full version has you deal with a bunch of functions that we don't really care about. We care about nice, well-behaved functions. Okay? So here's the intuition. So I want to show that f prime of... I'm going to show that f of g prime of x equals f prime of g of x times g prime of x. So my intuition is this. My intuition is exactly what you'd think. So if g of x equals u and f of u equals y, then my intuition is going to be that the change in y over the change in u times the change in u with respect to the change in x equals the change in y with respect to the change in x. So that's my intuition. How do we feel about the intuition? 1 to 5. Okay. Now my strategy for this proof, and this is the one place where I really need the t to x definition. It makes life so much happier. My strategy is going to be to use the t to x definitions and multiply the rabbit. Now, here's the rabbit. And this is just like, this is not a thing, right? Change in u over the change in u equals g of t minus g of x all over g of t minus g of x, which equals 1. So I'm going to multiply by 1. Instead of adding 0 like we did for the power and the quotient rule, I'm going to add 1. Multiply 1, not add 0. Multiply 1. Okay, so here's how it works. And again, this is not, I'm assuming here, note, I am assuming change of u does not equal 0 near x. So I haven't done it in full power. I am making an assumption about the change in u. All right, so let's prove it. So I've got d over dx of f of g of x equals the limit as t goes to x of f of g of t minus f of g of x all over t minus x. Now I multiply the rabbit. And I get f of g of t minus f of g of x all over t minus x times, and here's the rabbit, g of t minus g of x all over g of t minus g of x. Now I'm going to flip, I'm going to move this over here and this over here. So what I wind up with now is the limit as t goes to x of f of g of t minus f of g of x all over g of t minus g of x. Excuse me, my computer is complaining it doesn't have enough juice. Times g of t minus g of x all over t minus x. Okay. Now I use the product law, and I get the limit as t goes to x of f of g of t minus f of g of x all over g of t minus g of x times the limit as t goes to x of g of t minus g of x all over t minus x. And this part here is g prime. Hide myself so that you can see the whole thing. Okay. This piece right here is what I'm looking for. And believe it or not, this is actually what I want here. All right. So what I'm going to do is say the following. Okay. Let v equal g of t and let u equal g of x. So now I've got the limit as t goes to x of f of u of f of v minus f of u all over v minus u. Now, I need to deal with this t to x business. Okay? But g is continuous at x. Because g is differentiable at x. Right? In other words, the limit, as t goes to x, I'm sorry. The limit, I'll write it here. The limit as t goes to x of g of t equals g of x. In other words, g of t to g of x as let me write that here. In other words, g of t to g of x as t goes to x. So, v goes to u as t goes to x. So I can replace this thing right here with v goes to u. This I just inherited from before. But this right here is the definition of f prime of u. And that's what I wanted. All right, how we feel about that proof, 1 to 5? That's a nice one. Now, again, this is not the full proof. I've assumed that g of t minus g of x does not equal 0. Okay? Near x. So I'm assuming that if I get sufficiently close, it's not too badly behaved. I can get around that assumption, but it's not very intuitive the way you do it. And it doesn't really add anything. Okay, well, it doesn't look like anyone's watching at this point anyway. Okay. All right. So this actually gives us a very nice way to prove the quotient rule. And that's in your notes, but that's part of your problem set. So you can use this. That's the part of the point of problem set 6. You can also, I think, find it in the notes. Yes, you can. All right. Any other questions? One person's here. Yes. I probably lost you with the proof, but yes, you're still here. All right, so let's talk about mixing rules. Okay. So let's say that I want to do the derivative do d over dx of x squared sine of x squared. All right, so what here is the journey of x? Well, let's see. X is going to come in twice. I've got two places where I put in x. So I've got two x's. Now, on both of them, x is going to get squared. But notice something else happens to this x. This x also gets signed. Then they both get shoved together in a product. So what I'm going to do, this is the journey of x. And what I'm going to do is I'm going to work up. So the thing that happens last is this product. So what I'm going to do is I'm going to work up. So I've dealt with the, I'm going to deal with the product first, and I'm just going to work up. So the outer thing that gets done here is a product. So what I'm going to do first is the product. So I have the derivative with respect to x of x squared times sine of x squared plus x squared times the derivative with respect to x of sine of x squared. So that's here. Now I'm going to move up. Now, I'm only going to peel this one layer at a time, but these things are now separate problems. This is baggage, and these are two separate derivative problems. So I've got the next layer. I'm going to do this problem and this problem at the same time, where I'm going to chain this at the same time I deal with that. So what I'm going to do is I'm going to write u here. U will equal x squared. That x squared, not that x squared. And now I'm just going to deal with the problem. I have a chain, I have a power here and a chain here. And I'm going to do 2x and then carry some baggage. Plus x squared baggage. Now I'm going to deal with this. I'm going to have the derivative with respect to u of sine of u times the derivative with respect to x of u. All right, we're going to have to do some baggage. We're going to evaluate this derivative, and then we're going to sub in that u. So we got 2x times sine of x squared plus x squared times, now this derivative right here is cosine of u times the derivative with respect to x of u, which was x squared. Now I got a bunch of baggage. I'm going to go ahead, because I know this is going to be my last step, I'll go ahead and sub in there. And now I got to deal with this. That becomes 2x, and I am done. How do we feel about that one, 1 to 5? Okay? Let's deal with another one. Okay, now here's what the journey of x is. Look, I've got the same thing that happened before, right? I've got x in two places. So we need two x's. Someone needs to make me a meme where, it's Journey, as in the old band for X, So someone get on that meme. So I have the journey of X. So I've got X is going to go in twice. Now, the first thing that happens to this X is he gets logged. Whereas this X over here gets squared. Now they get multiplied together. And then they get signed together. So what is the outer layer of this onion? The outer layer is a sign. The last thing that happened is a sign. Okay. So I'm going to deal with that first. The chain, I move up. This, I deal with you first. I work outside in. All right, so the way I'm going to do this is I'm going to go D over. So the first thing that's going to happen is a chain. I'm going to call this whole kit and caboodle U. Okay. And then I'm going to chain it. So I've got chain of D over du, sine of u, times D over dx of u. And that I'm going to evaluate is just cosine of u times D over dx of ln of x times x squared. Now notice this is baggage, and now I have a product rule problem. So I'm going to carry my baggage, and I'm going to deal with the product rule. Now, note the big thing, because I'm multiplying by everything. Now I've got d over dx, ln of x, times x squared plus ln of x times d over dx of x squared. Carry my baggage. And I'm going to have 1 over x times x squared plus ln of x times 2x. And then simplify if you so desire. This would be cosine, sub back in, ln of x times x squared times the quantity, x squared over x is x, plus ln of x times 2x. You did not need to do this, but you did need to do that. 1 to 5, how do we feel about that one? Okay, that's a long one, but it's a good one. Okay, so what are the big takeaways from today? Oh, and I can't have things unevaluated. Let me do that real fast. Example of unevaluated term. So I can't have things where I just leave something unevaluated. Let me show you what I mean. So let V move with X. Okay. Take D over dx of sine of V. Okay? So that equals, I'm going to do a chain. I'm going to call this bit U, because that was the outside. The journey, by the way, of X would be X goes to V. Don't know what happens there. Goes to sine of V. Goes to sine of V. So now I've got a chain. I'm going to do the outside, d over du of sine of u times d over dx of u. So that's going to give me cosine of u times d over dx of sine of v. Now, I don't know anything else about v, but what I'm going to do is I'm going to apply the chain again. Okay, you'd think that there's nothing more I could do, but I can. I can deal with this a little bit. I'm going to have cosine of u times, now this is important, d over dv sine of v times d over dx of v. And that's going to be the cosine of u times the cosine of v times dv over dx. And I can't say anything more because I don't know anything more. And then I'm just going to sub back in my baggage. My u's. So this has become sine of v times cosine of v times dv over dx. How do we feel about that one, 1 to 5? Okay. Okay. So the big takeaway. Those are the two takeaways. When you're doing the chain rule, figure out what the journey of X is. For all these rules, figure out what the journey of X is, and then do one and only one layer at a time. One layer at a time. Next time we are going to do implicit differentiation. If you have any questions, I have office hours, and that's it for today. Lightning play in 1 minute. We can skip the Canadian national anthem. They're playing in Edmonton, so they'll sing it, which has already bugged me, okay? Has anyone noticed that the Americans start every hockey game singing a song about a war with Canada that we lost? Not the Canadian national anthem. The American national anthem is a song about a war with Canada that we lost. Just saying. Anyway, that starts in 1 minute. Are there any other questions? Okay, well, that's it for tonight. Thank you very much for watching, and I will see you next time.